Our sun is pretty big. It's so big that about 1 million Earths could fit inside. But how does our life-sustaining ball of plasma compare to some of the giants out there? When you start to think about it, the scale of it all becomes almost incomprehensible. Some stars are 1,000 times larger than our sun. Others are millions of times larger. And the biggest are nearly 10 billion times larger than a sun that's already 1 million times the size of our pale blue dot. Welcome back to Factnominal. Today, we're exploring some of the largest stars in the universe and whether or not they should even exist. Astronomers measure a star from its photosphere, or the outer surface of the star from which light is emitted. They compare the size of the star to our own sun using a term called solar radii. So if you have a star that measures 10 solar radii, that means 10 suns would line up neatly across its diameter. According to theoretical models, a star should max out at 1,500 solar radii. This is mind-numbingly large. Stars that have a big radius of around 648 million miles. If you compare by volume, 800 million suns could fit into a star that big. But we found a couple stars that are even bigger. Up until recently, astronomers thought that the largest observed star was UY Scuti. UY Scuti is a part of the constellation Scutum in our Milky Way galaxy. It's not visible to the naked eye because it sits in a part of the galaxy whose stars are blocked by light from the Milky Way's core. But astronomers found it back in 1860, and it has turned out to be very, very big, nearly 10,000 light-years away from Earth. UY Scuti was thought to have a solar radius of 1,700, with a margin of error of about 200. That means about 5 billion suns could fit inside it. UY Scuti has a circumference larger than the orbit of Jupiter around the Sun. It's so big that some hypothetical object traveling at the speed of light would take 7 hours to travel around it. If there was a planet orbiting Scuti, it would have to be over 600 astronomical units away from the massive Sun. 1 astronomical unit is the distance from Earth to our Sun, about 93 million miles. To put into perspective just how far 600 astronomical units is, Pluto is a mere 39 astronomical units away from the Sun. However, recent measurements from the Gaia Space Telescope have thrown a wet blanket on the hype surrounding UY Scuti, revealing that it might only be some 5,000 light-years away, making its solar radius around 755. Still huge, but nothing compared to Stephenson 2-18. In 2021, Stephenson 2-18 took the crown as the largest known star. Like UY Scuti, Stephenson 2-18 is also in the constellation Scutum, but it's a lot farther away, some 19,000 light-years away from Earth. It's part of a cluster of 26 supergiant stars in the region called Stephenson 2, but is brighter, larger, and more of an outlier than any of its brothers and sisters. If the distance of Stephenson 2-18 is accurate, it means it measures in at a whopping 2,150 solar radii. That's 10 billion times the volume of our Sun. Its circumference would reach farther than Saturn's orbit around the Sun. An object traveling at the speed of light would take 9 hours to make a complete loop around Stephenson 2-18. What's more, Stephenson 2-18 is relatively young and it's still growing. If this is true, then it could be on its way to transitioning into a luminous blue variable star, an incredibly rare type of hypergiant star that occurs when a supergiant ejects its outer layers and becomes incredibly unstable and variable in luminosity, but doesn't quite supernova. Instead, luminous blue variable stars undergo giant outbursts that resemble mini supernovas and are sometimes called supernova imposters. Stephenson 2-18 could also turn into a Wolf-Rayet star. These stars have completely lost their hydrogen and emit about 10 suns worth of material every million years. As their cores collapse, they can either burst into supernovas or condense further into black holes, depending on their masses. One of the most puzzling things about Stephenson 2-18 is its intense luminosity. It's 440,000 times brighter than the Sun. This is a number that was thought to be impossible based on the Eddington limit of luminosity, which is around 320,000 times that of our Sun. The Eddington limit is basically the maximum luminosity or brightness a star can achieve without bursting apart by balancing itself in a state of hydrostatic equilibrium between the outer force of its radiation and the inward force of its gravity. How can Stephenson 2-18 be so big and so bright, somehow defying the mathematical models of the universe? Before we answer that, let's see how it could get so big in the first place. Stars are born from interstellar dust clouds that can be hundreds of light years in diameter. At first, these clouds are cool and diffuse and consist mostly of hydrogen and helium. Over time, gravity pulls more and more atoms together within the cloud, adding to its mass. If a cloud becomes massive enough, it becomes unstable and undergoes gravitational collapse. As the cloud collapses, it gets hotter and hotter as hydrogen and helium atoms pack tighter together within the core of the cloud. More mass means more gravity, which sucks in more and more cosmic material in a process called accretion. A protostar begins forming. Cloud collapses usually result in hundreds to tens of thousands of stars forming almost simultaneously, creating embedded stellar clusters, basically a bunch of stars still surrounded by the remnants of their mother cloud. There are a few situations that can trigger the gravitational collapse that leads to the birth of stars. Helium and hydrogen aren't enough to collapse a cloud. There needs to be traces of other heavier elements. These can come from the remnants of older stars that have gone supernova and sent shocked matter into the clouds at high speeds. The collision of entire galaxies produce enormous amounts of energy that trigger starburst formations as the gas clouds from each galaxy are squashed into each other. Jets from supermassive black holes have also been proposed as stimulating star formation, injecting energy into the stellar cloud and catalyzing its collapse. Whatever the cause, at a certain point, the atoms within the condensing cloud become so tightly compressed that they're stripped of their electrons, leaving highly charged ions with exposed nuclei. The rapid compression and super high temperatures of these exposed hydrogen and helium nuclei sets off nuclear fusion, which creates a star's fusion plasma generator. Once the star has stopped collapsing in on itself and nuclear fusion is humming within its core, the plasma of the star starts to expand. However, the expansion is counteracted by the star's own gravity, and the plasma is pulled back in. Hydrostatic equilibrium is achieved, which we mentioned earlier, where the star's gravity and its radiation pressure equalize. This results in a more or less stable star. Stars are then maintained by a continuous series of explosions as hydrogen is fused into helium. Our Sun fuses a remarkable 620 million tons of hydrogen into helium each second. But how does a star become a giant? One of the factors is the composition and size of the gas cloud that form the star and the initial size of the protostar. Once a protostar has settled down, it becomes what's known as a main sequence star. These stars can range between 1/3 to 8 times the size of our Sun. Throughout a star's lifetime, it burns through hydrogen as it fuses into helium within its core. In some of the larger main sequence stars, this process is faster because they burn through their hydrogen faster. In smaller stars, it happens more slowly. It can take anywhere from a few million years to a few billion for a star to exhaust its hydrogen supply within its core. Once a star burns through its hydrogen supply, it's left with a bunch of helium. Helium takes a lot more energy and higher temperatures to fuse, which the star doesn't have. So the star begins to actually contract as its hydrostatic equilibrium is thrown off and gravity starts compressing in. When it does, the core is heated up again as more matter is pulled in. Additional hydrogen is sucked in towards the core and creates a shell around the helium center where fusion resumes. Then something called the mirror principle occurs. As the inner core within the shell contracts, the layers outside the shell expand, and the star becomes hundreds of times larger, meaning the core becomes hot enough to start fusing helium to carbon. When this happens, a massive amount of energy is released, ballooning the star into a red giant. This is what will eventually happen to our Sun. However, because the Sun is only a medium-sized star, it would balloon into a red giant, eject most of its gas, and then compress into a white dwarf. Stars that are at least 8 times the size of our Sun can undergo an additional stage, where they become supergiants. If they have enough mass, these large stars can begin fusing their carbon cores into even heavier elements like oxygen, sulfur, and silicon, creating yet even more energy that powers a further expansion, creating some of the largest stars in the universe, stars like Stephenson 2-18. So how can a star like Stephenson 2-18 exist if its luminosity and size seem to exceed the limits proposed through the mathematical equations of the Eddington luminosity limit and stellar evolutionary theory? The first answer is the simplest. We might have gotten the measurements wrong. Calculating the distance and luminosity of a star is pretty complicated. Determining a star's radius requires 2 initial observations: its angular diameter, which is how large it appears from Earth, and its actual distance from Earth. The angular diameter is easy enough to calculate, but determining precisely how far away a star is from Earth is actually very difficult. Interstellar radiation plays with the light from a star as it comes towards us. Also, many giant stars like UY Scuti and Stephenson 2-18 have variable fluctuating luminosities and expel huge amounts of gas, making them tough to see. The light from our own Milky Way galaxy also obscures many stars, again making them tough to see. For nearby stars, astronomers use what's called parallax to determine a star's distance from the Earth. Parallax works like this. Say you're looking out at some trees and distant mountains from the side window of a car as it drives down the road. You'll notice that as you drive along, the trees seem to be moving faster than the mountains in the background. The same thing happens in the sky. Nearby stars seem to move faster across the sky over the course of a year. By taking one measurement of a star's position and then another measurement 6 months later to calculate the star's distance based on its angle. But parallax measurements are only accurate up to a distance of about 400 light-years. For more distant stars, astronomers have used the spectral data of the stars we can measure through parallax to figure out 2 elements that can help estimate a distant star's solar radius, luminosity, and temperature. Nearby supergiants tend to have a lower temperature and a red hue, and astronomers take that data and project it onto more distant stars like Stephenson 2-18. In short, it's not the most perfectly accurate system, but it's still pretty effective. So if the measurements are correct, our model of stellar evolution seems incomplete. The answers to why these supergiant stars are so luminous might have to do with a phenomenon called going super Eddington. The Eddington limit is the maximum luminosity a star can achieve while in a state of hydrostatic equilibrium, when there's a balance between its internal pressure radiating outward and the gravitational force pressing against it from the outside. If you remember, any star larger than 1500 solar radii should simply burst into a supernova. But Stephenson 2-18, with its 2150 solar radii, hasn't. However, there are several ways a star can potentially go super Eddington and become even more luminous while still retaining its shape. The first is a theory called atmospheric porosity. It imagines an atmosphere around the star where there are dense regions surrounded by less dense regions. This would basically contain the mass loss of the star to the outer layers, producing more intense luminosity while the denser inner core of the star remains intact. Another explanation has to do with what are called photon bubbles. Photon bubbles are radiation-driven instabilities in the stellar atmosphere. They are proposed to develop within a highly radiated star where the radiation pressure is higher than its internal gas pressure. Basically, these bubbles are capable of transporting photons, light, at faster, more efficient rates and allow massive stars to glow brighter. There's a whole lot of uncertainty regarding the largest stars in the universe. For now, Stephenson 2-18 takes the cake. But as we develop better satellites and are able to look farther into the cosmos with more precision, there seems to be no limit to what we may find. Thanks for watching. Don't forget to like and subscribe for more fact-nominal content.